Welcome to the lesson 28 of industrial instrumentation. In this particular lessons, we will study optoelectronic sensor. In fact, the optoelectronic sensors I have divided in the two lessons, in the optoelectronic sensor 1 and optoelectronic sensor 2. In the optoelectronic sensor 1, we will look at these various types of photoresistors, then photodiodes, transistors we will cover very brief, and all these things. Also some brief introduction to fiber optics, because as you know that there are as the day is going on, so there are a lot of fiber optic sensors coming up, and we should discuss that details in the lesson 29, but in basic introduction to the fiber optic sensor also will be fiber optics techniques, transmission techniques, and all these things will be covered in this particular lesson. That is the second, latter part of this lesson 28. Let us look at optoelectronic sensor 1. Contents are photoconductivity. We will consider here photoconductivity. Based on that, will the photoresistors or light dependent resistors has been developed, and which is used extensively in instrumentation. So that will cover in the basic principle of the photoconductivity. Then based on this, what are the different photoresistors we have developed, engineers and scientists develop, that we will discuss, right. Then we have photoresistor, photodiode, then and applications. We will look at some of the application, typical application, that means how we can utilize, make some measurements, basic measurements. There are various applications of these photodiodes, but so far as the instrumentation is concerned, in context of instrumentation, we will take two examples and see how these photodiodes are utilized to make that type of measurements. Also, we will cover the introduction to fiber optics. We will discuss the fiber optics in details and fiber optic sensors in lesson 29, but basic principles of the fiber optics will be covered in the lesson 28. Photoconductivity. What is photoconductivity? The conductivity of a material is proportional to the concentration of charge carriers present, right. You know, conductivity is basically depends on the charge carriers. In the case of metals, we have some fixed amount of charge carriers which is thermally generated. In the case of semiconductor devices, these can be varied depending on incident light, so which will change the resistance. Obviously, the photocurrent also will change. The current density in amperes per meter square will be expressed as follows: I equal to n mu n plus P mu P E multiplied by E, where n is the magnitude of free electron concentration, P is the magnitude of hole concentration, sigma is the conductivity, mu n is the electron mobility in centimeter square upon by volt second, and mu P is the hole mobility in centimeter square per volt second. Now, sigma conductivity will be given by n mu n, this is mu n, okay, this is mu n, P plus mu P multiplied by E, where E is the electronic charge, E is electric field. Okay. For intrinsic semiconductor, that is semiconductor without any impurity, we call it intrinsic semiconductors. In the case of that means without any doping. Once you dope, what will happen? The number of hole electrons will change. Now, if you dope with a p type impurity, number of hole will increase. If you dope with the n type impurity, then number of electron will increase, right. So, for intrinsic semiconductor, n equal to p equal to ni, okay, which is called the intrinsic concentration. When the semiconductor is doped, we call it extrinsic semiconductor, right. In that case, NP cannot be same, because it depends on the what type of dopings. It might be in the case of trivalent impurity. What will happen, that you will find that the hole will increase, number of hole concentration will increase, so on and so forth. Radiant energy supplied to the semiconductor causes covalent bonds to be broken, and hole electron pairs in excess of these generated thermally are created. Excuse me. These increased current carriers decrease the resistance of the material. Okay, whenever the light falls, there is increase of charge carriers. Okay, in fact, what will happen, there is, as you know, there is in a metals we have a forbidden energy. So some some electrons will cross that forbidden energy gap and come to the conduction level. So which will contribute to the change of concentrations of the charge carriers. Hence, such a device is called the photoresistor or photoconductor. Clear? For a light intensity change of 100-foot candle, the resistance of photoconductor may change by several kilo ohm, right. The minimum energy of photon required for intrinsic excitation is the forbidden gap energy. Okay. Now, electron volt, which is in electron volt of the semiconductor material. Okay. If you remember, when it appears to be like this one. I have a conduction band. Okay. So when the light falls, okay, which is comes here, some of the electrons, this is the forbidden gap energy Eg. So this energy, this amount of energy must fall, so that the electron will come to the conduction band. This is the conduction band. Okay, and this is our forbidden gap energy. Right. Now, threshold wavelength of incident light, that means the light which will be sufficient to generate the excess carriers in excess to the thermal energy, is given by 1.24 by Eg in microns or micrometers. For silicon, Eg is equal to 1.1 electron volt, for lambda c equal to 1.13 micron, and for germanium Eg equal to 7.2 electron volt, 0.72 electron volt, which will give you lambda c or the incidence of that, because this is necessary, because you must know what the incident light will be make this incident frequency of the incident light, which will you must fall on the semiconductor devices, photoelectric devices, so that the excess electrons or excess carriers will be created, right. Photocurrent. Now, steady state current is given by I equal to E multiplied by PR into tau upon T subscript small t. What are these legends? This is steady state current in a photoresistor or photoconductor, where PR is the rate at which the carriers are produced by light. Okay, rate at which the carriers are produced by light, because if the light falls, strong light falls, more number of carriers will be generated, which is in excess of the thermally generated carriers. Tau is the average lifetime of newly created carriers, because you see that whenever the whole electron pair is generated, there is a chance of recombination. So this is the average lifetime, because once it is recombined, that current cannot be detected at the output. T subscript small t is the average transit time for carriers to reach the ohmic contact, because any semiconductor devices, I must collect the current at the outside, so that it must reach, that carriers must reach the ohmic contact, so that it will pass through some ammeters and some detectable current will be observed. And E is the electronic charge, E is the electronic charge here. Okay. Now, one of the commercial photoconductivity cell is cadmium sulphide, one of the most widely used photoconductivity cell of photoresistors or LDR, whatever the name you call, is light dependent resistors or photo resistors or photoconductivity cell. Basically same, that means it is made of cadmium sulphide with pentavalent antimony impurity. Impurity must be there, otherwise it cannot be pentavalent impurity. Obviously, the charge carriers will be here the electron, right, since it is pentavalent. The resistance is over 2 megohm in the dark and 10 ohm in the bright light, right. It looks like this, if I take it. So, it looks like this. I mean, if you look at the encapsulation, I have drawn a little bigger. 2 leads are coming up, and they have a transparent plastic cover on the top, unlike the other semiconductor devices, and you can see these photo resistors inside, right. So, light should fall on this one. If you bring it to the sunlight, you will find immediately the resistance, if you measure the resistance across these two, immediately it will reduce, right. That resistance you can make several circuits by which I can, suppose if I have a circuit like this one, I am giving a voltage of suppose 5 volt, and this is my photoresistors, okay, this is my photoresistors. So, light is falling on this, okay. So, what will happen? So, the current will change. So, I can do in other way, we can treat, I mean I can do it another way. Okay, I can take a new slide, there is no problem. So, it will go. So, let me take the pencil again, let me take a new. So, it looks like this. I can take a right. So, I am giving a 5 volt here, and this is my photo resistors, light is falling on this, okay. Looks like, as I told you earlier, it is encapsulations. So, it looks like this, 2 leads are coming up, and we can see the photoresistors here, lights are falling on this, right. And this voltage, obviously what will happen if the light falls, you will find that this voltage will change, right. So, if I measure, because this resistance will change, so this voltage VO across this will also change. So, this VO can be utilized for making so many sensors or switches also, right. I can use it as a switch also, this photoresistors, clear, because this voltage will change as the light falls on this. In dark it is very large resistance, around 2 mega ohm, in the bright light it is very less, 20 ohm, clear. In fact, the dark it should be very high, it should be infinite, but there is always a dark current, because there will be always some electron hole electron pair in the which is thermally generated. So, there will be some current, right. So, resistance is over 2 mega ohm in dark and 10 ohm, 10 to 20 ohm in bright light. Cadmium sulphide has a high dissipation capability, excellent sensitivity in the visible spectrum. Power dissipation is more than 300 milliwatt, and a selenium cell, selenium is also used as a photo resistor. Selenium cell is sensitive throughout the visible and particularly toward the blue end of the spectrum, right. Now, semiconductor photodiode, now we talk about only the photoresistors. So, that means I have some means that the light dependence resistors we are calling also it, also as a light dependent resistor, but more applications in instrumentation you will find is that is in the semiconductor photodiode. Photodiode and phototransistor is almost same. In case of phototransistors, I will get some amplification, but the time constant is large, whereas in the case of photodiode current is small, but the time constant is small. If a reverse bias PN junction is illuminated, the current varies almost linearly with the light flux. The effect is utilized in the semiconductor photodiode, right. This effect is utilized in the semiconductor photodiode. The reverse saturation current IO in PN diode is proportional to the concentration PNO and NPO of minority carriers in the N and P region respectively. Okay. If you have a reverse bias photodiode, then in that case you know there is no minority carriers. So, the only the majority carriers will not play the current, because only the minority carriers will play a key role to have a current, because in all semiconductor it does not matter. If it is p type semiconductor, the hole is the majority carriers and the electron is the minority carriers. In n-type semiconductor, electron is the majority carriers and the hole is the minority carriers. So, if it is reverse bias, then what will happen, that the reverse saturation current IO in PN diode is proportional to the concentrations of PNO and NPO of minority carriers and the N and P type region. You see the PNO, we are calling the minority carriers in N type region, and NPO is a electron which is the minority carriers in P region respectively. And the volt ampere characteristics will be given by I equal to IS plus IO 1 minus E exponential to the power V by eta Vt. Please note this is eta, right, this is not N, this is eta, like this one, where Is is the short circuit current and it will be proportional to the light intensity current under the large reverse bias. V is positive for forward bias and V is negative for the reverse bias. Right. Now, for the if the reverse bias is large, then obviously what will happen, this part will be very small, is not it? If the reverse bias is very large, so what will happen? If reverse bias is large, then what will happen, you see that this will be negative. So, this if this is V is very large, then what will happen? So, this will be almost negligible and only it will be I equal to Is plus IO, where Is is a short circuit current and it will be proportional to the light intensity current, and large reverse bias V is positive for forward bias and negative for reverse bias. The parameters eta, I should write here beta, is unity for germanium and 2 for silicon. Okay. This eta, this is not N, please note eta. The parameter eta is unity for germanium and 2 for silicon, and Vt is the volt equivalent of temperatures, right. Now, this is a equivalent circuit of a reverse bias photodiode. You see this, we have one capacitance, we have a current generator here, okay, C equal to 10 picofarad, P is R is quite large, 50 mega ohm, and there is a small resistance R equal to only 100 ohm. So, Is, that saturation current, is equal to K into L. What is K? We will see. The symbol L represents the light lumens, light flux in lumens. Okay. You see the Is equal to KL. The symbol L represents the light flux in lumens, and K is the proportionality constant in the range of 10 to 50 milliampere per lumen. Clear? And the reverse saturation current IO doubles for every 10 degree centigrade. Okay. Reverse saturation current, we have seen also this one into 4. Reverse saturation current IO doubles for every 10 degree centigrade, and its typical sensitivity is 10 milliampere per lumen, right. The lumen actually is defined as a 1 watt of light at lambda equal to 0.55 micron can produce 680 lumen. This is a standard for lumens. That means a 1 watt of light at lambda equal to 0.55 micron can produce 680 lumens. Okay. Now, you see this is a photodiode characteristics we have drawn here. This is a diode current in microampere, and this is the reverse voltage. As you increase the reverse voltage, you will find that there is saturation, and this is the incident light which is given in foot candle, right. This is incident light in foot candle, 3000 foot candle, 2000 foot candle, 1300 foot candle, 335 foot candle, this one, and there is a dark current. Even if you do not throw any light, okay, on the diode, okay, this basically you are sending a light to the junctions of the photodiode. Please remember, right, PN junctions. So, the PN junctions you are sending the you are throwing the light. So, this is the dark current, right. This is the reverse bias photodiode characteristics, reverse voltage V, and there is a diode current. So, as you can see that if you increase the light, obviously your diode current also getting increased. 1 lumen per square feet is equal to 1 foot candle. 1 lumen per square feet is called the 1 foot candle. NPN phototransistors provide electrical amplification, but has a larger time constant. Okay. So, you will find that this photodiode is basically a diode, okay, but you will find that it's put in a plastic encapsulation so that the light can fall on the p-n junction. Okay, p-n junction. It is more sensitive than the photodiode, otherwise the basic principle is same as the photodiode. It is more sensitive, large current you will get because you will get some amplifications. It is inherent to any transistor's characteristics. Suppose if the base emitters we throw some light, so obviously at the collectors we will get a large current with amplifications. That is the only advantage, but time constant is large. Some typical applications of these photodiodes, let us look at some typical applications. Now, this is a scheme which we have shown that a digital revolution counter using photodiode. How a digital revolution counters we can make using the photodiode, you see here. So, I have a light source, okay, light source is coming here, this is a disk, okay. When this light source, light emitting diode, then this hole on the disk, this circular disk and the photo detector which is photodiode comes in a one line, then only some light will fall on this one, okay, light will fall on this photo detector, otherwise not. So, you see if it rotates, if this disk rotate, as there is a shaft and the disk is rotate, for each rotations I will get a pulse here at the output of the photo detector. Now, this type of pulse, as you know, this type of pulse will be very irregular shape, right. So, this pulse is very irregular shape. This pulse will be very irregular shape. So, you must send to a Schmidt trigger, okay, to which is called a pulse shaper to give a regular shape pulse and then to a counter. So, as the speed of this disk increases, okay, number of count per second or per minute will also increase, right. So, I can make a direct RPM meters or a revolution per minute meter by this type of scheme. We have some other electronic circuitry, but this is some applications of the photodiodes. There are numerous applications that is not much concerns with the instrumentation or measurement, that is I am not discussing. Automatic opening of the doors and all these things, you know, okay. Automatic switching on the street lights. In many countries you see that there is no person to switch on the street lights. So, what they do, there is a photo diode sensitive switches they have. So, what will happen that when the light, when the sunlight goes down, so automatically the photodiode will be activated and it will turn on the switches of all the street lights, okay. So, there are some that type of many applications are there, especially in countries like Europe. You will find that when the trams and trains are going, usually to save the power, they do not turn on the lights inside the bus or tram. So, whenever the tram or bus going inside a tunnel, so obviously the light is less, all the lights inside the tram or bus should switch on. So, those are photosensitive, but that is not much of the instrumentation there. Some measurement techniques we are discussing, that means some revolution counters we are using, we have developed using the photodiode. Let us look at how it works. So, you see this is the circuit schematic of the revolution counter. Here you see that we have a 7490 decade counter. Most significant bit of the 7490 is going as a clock. Here is a clock which is coming from the AND gate. Okay. Again, the most significant bit of the 7490 is going to the clock of the next 7490. Clear? So, it is a decade counter, it will start from 0. This is a decade counter, it will start from 0 and will come up to 9, then again comes to the 0. So, it is 10 different states. So, modulo 10 counter, so it will start from 0, count up to 9, then again come to 0, right, like that. Now, how it works, you see this is 7475 is basically a D-latch 4-bit D-latch flip-flop. You know, the D-latch is basically a device which is basically a master slave flip-flop, but it will latch to the previous state until unless new clock comes, right. Whenever a clock cycle comes, whatever you have at the, so sometimes we call the data latch flip-flop, that is the reason we call D flip-flop or data latch flip-flop. Data latch flip-flop means whatever the previous signals we have, so it will stick to that until unless a new signal comes, new state comes, either it may be 0 or 1, it will go back to that, it will go to that particular state now it is basically when the clock pulse comes at the trailing edge of the clock pulse. In the case of master slave, obviously it should be activated at the trailing edge of the clock pulse, So, it will go to the state. If it is 1 is the input of the D flip flop, this is basically JK flip flop, you know, this is basically JK flip flop. The data which I want to transmit, that data is directly coming to the J input, and data and the K input is whatever the data is coming in the J inputs, we are passing through an inverter and coming to the K input, right. So, automatically what will happen, see if it is 1 is coming, so the J input is getting 1 and K input is getting 0, and if the 1 is 0 is coming, J input is getting 0 and the K input is getting 1, so it is inverted. So, what will happen under the clock pulse, if it is a master slave to the trailing edge clock, it will trailing edge clock activated. So, what will happen that entire change will occur at the trailing edge, and your whatever the data input you have, either 1 or 0, it will stick to that, right. Now, 7475 is such a data flip flop with a 4-bit data latch flip flop. 7475 is a 4-bit data latch flip flop, okay, is a 4-bit. So, what will happen, you see, it is very interesting. You see, I have in the AND gate inputs, we have a clock pulse, high frequency clock pulse, right, and you see here. Now, this clock pulse is coming from where? It is coming from the photodiode. Depending on the number of speed, depending on the speed of the disc, okay, number of clock pulse per minute will also increase, right. So, what we are doing here, you see that in one input of the AND gates, I am giving this clock pulse, in other inputs I am giving a pulse where the mark is 1 minute, okay. Then it will have something, then again it will come. So, it is only 1 minute width, it is repeative pulse obviously. Now, what will happen, you see, so this whenever this is high, so it will activate it and the counter will start to count from 0, right. Now, you see what will happen during that time, this is inverted here. So, 7475 will not be activated. So, counter is going on counting. Now, what will happen at the trailing edge of this clock pulse, when the 1 minute is over, so this pulse will go down and no more it will no more this output from the photodiode can enter the 7490. So, 7490 will stop counting. During that time, when this is low, this will be activated because it is inverted, okay. So, what does it mean? So, whatever they have counted so long, okay, that through 7475 it will come to the BCD 7 segment decoder and then to the display unit. Clear? We have a 7 segment display, so it is in the display unit. Now, during that time, you see what will happen, these durations I can make very small, okay. I can make 1 minute, then 1 second, again 1 minute type of pulse I can make it. Clear? So, during that again what will happen, whenever this pulse is up, next clock. So, this whatever the data we have at the end of the 1 minute, that will hold for the next until unless next clock pulse comes. That is the reason it is called data latch flip flop. So, what will happen again? Again it will start to count. So, for 1 minute. So, after this, when this falls, it will stop counting, 7490 will no more count anything, okay. So, the one this falls, this will activate it because this will be 1. So, whatever the data we have at the output of the 7490 in the 4-bit, that will come to the 7475. So, previously it will latch to the previous values. So, then it will come to the display and it will do BCD 7 segment decoder, then it is in the 7 segment display, right. This way it will work. So, this you can see this one application, even though these photodiodes it has a very small part, but until unless you have a photodiode, this system will not work, you see. So, I have a light source, when the light source it is rotating in a very high speed, and since photodiode has a very small time constant. So, small amount of whenever a unit is speeds at a very high speed, it does not matter, it will detect each and every pulse. Whenever this photodetector, this hole and the light source comes in one line, so it will make one pulse, and this pulse is to be shaped through Schmidt trigger, then it is coming to the counter. Clear? This is our scheme. This is very interesting scheme, that is will be activated for 1 minute, will count for. So, whatever the reading we are getting here, it will be directly in revolutions per minute, is not it? Because we have made the width of 1 minute. mark to space. Mark will be for 1 minute, space might be for 1 second, it does not matter. So, during 1 second what will happen? Again, until unless this 1 minute comes, at the end of the 1 minute, this data, whatever the data there, that will be displayed automatically, that will remain in the same hold position. Clear? Now, limitations, it has a limitation, lack of zero references, and it cannot sense the directions of the rotations, whether it is there, I mean the disc is rotating in the clockwise directions or anti-clockwise directions, it cannot sense. For that reasons, we have seen that we need some phase sensitive demodulation to have that type of sensing. Measurement of steel strip in hot rolling mill. Okay, this is another, I mean, a scheme by how the photodiodes can be utilized to make a, because in the hot rolling mill it is very difficult, it is so hot, temperature is so high, it is very difficult to measure the thickness of the, because thickness measurement of the rolling sheet is also very important. Accordingly, I can use the feedback force, so that we can put more pressure on the rolls, so that it should be thinner, or remove the pressure, so that it should come to the proper thickness, right. So, in context of that, we will see that the photodiodes, because a hot rolling mill in the hot surface will work as a photodiode, light emitting diode. Okay. Now, the question comes, we need little bit of mathematics, that means that autocorrelations and the cross correlation functions, that will be discussed now. You see the correlation function, the autocorrelation function of a signal is closely related to the power density spectrum of the signal. The autocorrelation functions of a form is defined as Rxx limit t tends to infinity 1 upon t, t to 0 xt, xt minus tau into dt. The waveform xt is multiplied by delayed versions of itself, xt minus tau, and the product is averaged over t seconds. The waveform xt is multiplied by delayed versions of itself, xt minus tau, and the product is averaged over t seconds. If it is multiplied by the same signal delayed by some time, we call autocorrelation function. Now, let us look at the cross correlation. The cross correlation function between the two identical waveforms xt and yt are given by Rxy t xt minus tau yt average, which is limit t tends to infinity 1 upon t, t to 0 xt minus tau yt into dt, right. The cross correlation function is used to measure the non-contact velocity measurement of rolled metal sheets, non-invasive type of techniques. Okay. So, non-contact method of the velocity of the rolling sheets, right. So, the velocity is most important, thickness is there, but the velocity is most important. Because why it is important? Because in the hot rolling mill, if it is not, if you do not put in a coil form when it is still hot, that will create problem, right. So, that is reason. This is a scheme for measurements of velocity of hot rolling strip, you can see here. So, we have a hot rolling strip here, you can see, or ingot is coming, so it is coming through a roll, and the thickness is getting reduced like this one. This is the thickness, and this is the velocity should be, as I told you, this velocity is to be maintained, because until unless it is hot, you cannot put in a coil form, right. So, that is the reason the velocity is important. We have a roller here, these two are called the rollers. Now, see this, since it is hot, so it will work as a source, light source. We have a collimeter lens, these two are the collimeter lens. Okay. So, light will be come and it will focus and will form the photocell. We have the two photocells here, one photocell here, one photocell there. We have a variable delay here. We are assuming these two signals are same type of signals, but it is not the exactly same signals. It is coming from the two different sources. So, we have to make the cross correlation function of these two signals. This is the correlators, which is make the cross correlations of the two signals, which is coming yt and xt, and the cross correlation coefficients we are getting here. The measurement of velocity of rolled steel of sheet material is difficult, particularly when it is red hot. The basic scheme of the correlation measurement is shown in figure 4, which I have already shown. The fluctuations of intensity of the light reflected from the metal surface are transformed into electrical signals by means of two photocells mounted at a distance d apart. Let us look at, yes. The cross correlation coefficient is a maximum when the variable delay equals the time for a point on the strip to travel between the measurement points. There are two measurement points. So, the cross correlation coefficient is maximum when the variable delay equals the time for the point on the strip to travel between the measurement points. Let us look at. You see, this is the measurement point. When this variable delay equals the time for the time to travel the same point to this, I will get the peak output of the cross correlation coefficient. Okay. So, let us look at that. The cross correlation coefficient is maximum when the variable delay equals the time for a point on the strip to travel between the measurement points. Now, the sheet velocity will be small d divided by tau d, because what we will do actually, you see here, actually I will vary the delay. So, whenever I will vary the delay, when I will get the peak, I will measure this tau d, right. So, tau d, so the d divided by tau d will give us, because this is a cross correlation coefficient, so it is a correlation coefficient. So, d divided by tau d will give you the velocity of the rolled steel. Now, let us come to the, with this way I come to the end of this one, that means that optical sense, the photoelectric and photoconductivity sensors, photodiodes. Let us come to the introduction to the fiber optic transmission system, because in the lesson 29 we will cover the fiber optic sensor, because otherwise it will be very huge. So, I will cover some of this in this lesson 28. Fiber optics is a technology of using light to transmit information. Light has a number of advantages over electricity as a medium for transmitting information. It is immune to corruption by neighboring electromagnetic fields. Two light sources can go parallelly, two cables can go parallelly, whether it is very difficult to put two cables parallelly, because there are chances of crosstalk, right. It is immune to the corruption by the neighboring electromagnetic fields. Attenuations, in all electrical circuit there is attenuations. Here in this case, attenuations over a given transmitted distance is much less, and it is also intrinsically safe, and since it is light, so there is no hazards as such. Fiber optic technology is used in two major ways. First, the fiber optic cable itself can be used directly as a sensor in which the variable being measured causes some measurable change in the characteristics of the light transmitted by the cable. Secondly, the fiber optic cable can be used as a transmission medium for data. Okay. The latter use of fiber optics cables for transmitting information can be further divided into three separate areas of application. First, relatively short fiber optic cables are used as part of the various instrument to transmit light from the conventional sensor to a more convenient location for processing, often in situation where space is very short at the point of measurement. Secondly, longer fiber optic cables are used to connect remote instruments to controllers in instrumentation networks. Okay. Longer fiber optic cables are used to connect the remote instruments to controllers in instrumentation networks, okay, because ultimately that signal is to be transmitted to the controllers, right. So, transmissions, electrical transmission, there is a lot of problems, so we can switch to the fiber optic sensors. Thirdly, longer links are still used for data transmission system in telephones and computer networks. We are not much interested, we will not, neither will cover that in, but this third one in more details, right, that is in the communication part. These three application classes have different requirements and tend to use different types of fiber optic cable. Principal fiber optics. The central part of a fiber optic system is a light transmitting cable containing at least one, but more often a bundle of glass or plastic fibers. This is terminated at each end by a transducer as shown in figure 5. At the input end, the transducer converts the signal from the electrical into light, right. This is, you see, I have a transducers which is electrical signal is coming from the left hand side, so it is coming the light is getting launched through this fiber optic cable, and basically you will see these fiber optic cables, light can transmit, can go in a car path. We know from our childhood light never goes in a car path, but you will see that using the total internal reflections in the fiber optic cables, okay, the light can travel the curved part also, right. So, at the transducers we will get light again. Suppose this is our LED light emitting diodes, it is launched through this one, and there is we have a photodiode or PIN diode. Okay. So, I will get the electrical outputs. So, the electrical to electricals I get at the two ends, whereas in the medium it is only light are taking them our data or information. At the output end, the transducer converts the transmitted light back into electrical form suitable for use by data recording, manipulations and the display systems. So, we have a data recordings, we have a conversions, whatever you like you can do once it is in electrical form. These two transducers are often known as the transmitter and receiver respectively. One is the transmitters that we have seen. Which one is transmitter? This is our transmit, this also transducers, but we are calling it transmitter, and these are we are calling it receiver, since it is receiving the signals. We are transmitting the signal through this LED, we are receiving that signal with the photodiode or PIN diode, we are calling it receiver. In that case, okay, sorry. These two transducers are often known as the transmitter and receiver respectively, and the arrangement described above is somewhat modified when the cable is used directly as a sensor. Okay, you will find in some cases we will use the cable as a sensor. So, we will modulate the light which is going through this one. So, it will be slightly different in that type of application. In that case, the light injected into the cable comes directly from a light source and does not originate as an electrical signal. However, the same mechanism described later have to be used to get the light into the cable. Fiber optic cable. Fiber optic cable consists of an inner cylinder core surrounded by an outer cylinder cladding as shown in figure 6. Okay. What is that figure 6? Let us look at a little, far it went. So, we have a inner core, we have a outer cladding, then jacket and all these things. Okay. The refractive index of this one will be higher than this one, then only you will get the total internal reflections. Please note, refractive index of this one of the inner core will be higher than the refractive index of the outer cladding. Clear? This is always, otherwise you won't get the total internal reflection. Fiber optic cable consists of an inner cylinder core surrounded by an outer cylinder cladding as shown in figure 6, which I have shown. The refractive index of the inner material is greater than that of the outer material, and the relationship between the two refractive indices affect the transmission characteristics of light along the cable. The amount of attenuations of light as it travels along the cable varies with the wavelength of the light transmitted. Okay, this is very important. We have seen that you have to find the optimum wavelength of light, optimum color of the light, which will give us the minimum attenuation. That is important, otherwise you have to use a repeater. Though I am saying that there is loss is less, but there is a loss usually which is described in dB per kilometer, something like that. So, what will happen as it is less, I need less repeater, otherwise again I have to convert that signal to at the repeater stations. I have to convert that signal in the electrical domain, again through LED I have to transmit that signal. This characteristics is very nonlinear, and a graph of attenuation against the wavelength shows a number of peaks and troughs. The position of these peaks and troughs varies according to the material used for the fibers. It should be noted that the fiber manufacturers rarely mention these nonlinear attenuation characteristics and quote the value of attenuation which occurs at the most favorable wavelength. Two forms of cable exist known as monomode and multimode. Okay. You have monomode fiber, we have multimode fiber. Monomode has some, monomode has a, launching the light in the monomode fiber is very difficult, because it is, you have to use a very directional light in the case of laser, whereas in the case of multimode fiber I can use ordinary light LED. That is very, saves a lot of cost. Okay. Monomode cables have a smaller diameter core, typically 6 micron, whereas the multimode cables have much larger diameter, typically between 50 micron and 200 micron. Both glass and the plastic in different combinations are used in various forms of cables. We can use glass or plastic. Okay. One option is to use different types of glass fibers for both the core and the cladding. Okay. You can use both the glass for the, but obviously of different RI, refractive index, for the core and cladding. A second, the cheaper option is to have a glass fiber core which has a higher refractive index and a plastic cladding, okay, which has a less RI value, refractive index value. This has the additional advantage of being less brittle than the all glass versions. So, obviously, if you use the plastic, so it will has, because ultimately you see the mechanical strength is also very important. If it is made of full glass, it is very difficult to hold it. I mean, it is very difficult to, it is very prone to the breaking. So, if you use the plastic cladding, obviously your chances of survival is better. Finally, all plastic cables also exist. Also, two types of plastic varies with different refractive indexes, but they have a larger losses. So, that is the reason all plastic cables is not very popular till now. This already I have shown you inner cross sections of the fiber optic cables, inner core. This might be all glass, this might be glass, this can be glass, whereas this can be glass and this can be a plastic. Obviously, the refractive index of this one, whether it is glass or plastic, it does not matter, obviously should be higher than this one. Or it can be used all plastic, but the all plastic is attenuation is large. So, that is another problem in the all plastic fiber optics cable. This is the cheapest form of all, but it has a disadvantage of having high attenuation characteristics, making it unsuitable for transmission of light over a medium of larger distance. For a shorter distance, okay. Suppose I am using as a sensor, pressure sensor, load sensor, that type of case not a problem, but if it is used for the transmissions only, so it is not very suitable for using the plastic, all plastic fiber optic cables. Protection is normally given to the cable by enclosing the same types of insulating and armoring material. So, we have outside plastic, I mean we have a like we have the electrical cable, that type of protections you will give. Protection is normally given to the cable by enclosing it in the same types of insulating and armoring the material that are used for copper cables. As in the case of copper cables, we have a several, because this will give you mechanical strength also. It protects the cable against various hostile operating environments, also against mechanical damage. Okay. So, mechanical damage, so that it will give you these protections, will give you that type of things. When suitably protected, the fiber optic cables can even withstand the flames. If you engulfed by the flames, fiber optic cables, we have observed that the fiber optic cables can survive, which is impossible in the cases of the copper cable and all those things. Fiber optic transmitter, let us come. The light emitting diode LED is commonly used as a transmitter, which converts, usually LED is used for the multimode fiber, but the monomode fiber we have to use laser. Please note, because the light should be very much directional. In fact, you will find the launching the light in a fiber optic cable is a very, very difficult task. We have a lot of connectors and all those things. So, if some way or the other that is simplified, okay, that gives you a lot of advantage, a lot of flexibility of using the fiber optic cable, which converts an electrical signal into light and transmits into the cable. The LED is particularly suitable for this task, and it has an approximately linear relationship between the input current and the light output. So, the input current and light output is very much, I mean this linear relationship is there. We have seen that the diode has the, that type of advantages. The type of LED chosen must closely match the attenuation characteristics of the light path through the cable and the spectral response of the receiving transducers. Okay, because receiving transducers also should have same characteristics, otherwise it cannot convert that light signal to the electrical signal. Thus, one-to-one characteristics should be there. That means, as I told you, linear characteristics, the what how amount of light falls and the current it is generated is linearly variable. So, that should be at the receiver end on the amount of current, amount of light fall, that is at the case of receiver end. In the case of transmitting end, the amount of current should be directly proportional to the amount of light which is going to launch through the fiber optic cable. An important characteristics of the transmitter is the proportion of its power which is coupled into the fiber optic cable. This is more important than the absolute output power. This proportion is maximized by making the purposefully designed LED light emitting diode transmitter, which have a spherical lens incorporated, so that it is like a, I mean, if you put a source at the focal point of a lens, so what will happen? The light which is coming out of the lens will be a parallel. So, that is very much necessary. So, this produces approximately parallel beam. You see whatever I said, this produces a, what is this proportion is maximized by making the purpose designed LED transmitters, which have a spherical lens incorporated into the chip during manufacture. This produces an approximately parallel beam of light into the cable with a typical diameter of 400 micron, right. The proportion of light entering the fiber optic cable is also governed by the quality of the end face of the cable and the way it is bonded in the transmitter, because this is a very difficult task, as I told you. It should be very much well polished. Okay. If there is a little misalignment, so that light cannot be launched through the fiber optic cable, because intensity of light should be sufficient, otherwise you need to repeat it very, I mean, after a short distance. In the case of transmission, instrumentation, that is not very much necessary. A good end face can be produced by either polishing or cleaving. Okay. End face of the fiber should be very much polished. Polishing involves grinding the fiber end down with a progressively finer polishing compounds until a surface of the required quality is obtained. Okay. So, end will be perfectly polished. So, okay. This means this end will be perfectly polished, because you see I have a cable. Okay. I have a cable and we have a, I have a cable and I have a transmitter here. So, whenever it is connected to the cable, this transmitter, this light cannot be launched if this end surface of the cable is very rough. So, that should be very much polished. So, we are using grinding technique, then cleaving technique. So, to that it will be very much polished and light can be easily transmitted to this one. This light source, as I told you, it is a spherical spherical lens, so that the light which is coming out from the, suppose the source is here, it is falling on the spherical lens, and the which is from the lens, when it is going out, it is going all parallel lines of lights. Okay. So, that will be launched to the fiber optic cable. Attachment to the transmitter is then normally achieved by the gluing. The proportion of the light transmitted into the cable is also dependent on the proper alignment of the transmitter with the center of the cable, right. The effect of the misalignment depends on the relative diameter of the cable, and figure 7 shows the effect on the proportion of the power transmitted into the cable for the cases of cable diameter greater than the beam diameter. You see, this shows that the some degree of misalignment can be tolerated except where the beam and the cable diameters are equal. Okay. The cost of producing exact alignment of the transmitter and the cable is very high, as it requires the LED to be exactly aligned in its housing and the fiber be exactly aligned in its connector and the housing to be exactly aligned with the connector. Okay. Therefore, the great cost savings can be achieved wherever some misalignment can be tolerated. That is the reason multimode fiber is always preferred over the monomode fiber. Okay, its little misalignment will not affect much. You see, this is the we talked about effect of transmission. Here see the fiber diameter is more than the beam diameter. Okay, we can see that how much tolerances, misalignments we can align. That is, a multimode fiber has always the more diameter is more, right. So, that is advantage, whereas the fiber diameter is equal to beam diameters and fiber diameter less than beam diameters. Whenever this is less, it is more, we have a small amount of misalignments only will be tolerated. Fiber optic receivers, a device used to convert the signal back from light to the electrical form is usually either a PIN diode or a phototransistors, right. PIN diode is more popular use. Phototransistor have good sensitivity, but only low bandwidth. The bandwidth of the phototransistor is very small. On the other hand, PIN diodes have a much higher bandwidth, but has a lower sensitivity. We need amplifications, obviously, that is not a problem. So, we can have an amplifier. If both high bandwidth and high sensitivity are required, then the special average photodiodes are used, but at a severe cost. Okay. The same considerations about losses at the interface between the cable and the receiver apply as for the transmitter, and both polishing and the cleaving are used to prepare the fiber ends. The output voltage from the receivers are very small and the amplification is always necessary, right. That is I told you. I mean I can use a PIN diode. If I use PIN diode, I need further amplifications, but that is the advantage which we are getting because it has a larger bandwidth, right. The system is very prone to noise corruption. Okay, as even though I am telling that it is not corrupted by any interfering noise or any electrical noise, but the noise will come at the transmitting and the receiving end, because there is a position, there is a where it is signals, optical signal is converted to electrical signal again. So, noises source will introduce there, even though if a fiber optic cables are going on and over there are many crisscross of the other electrical cables. So, any spikes in the electrical cable does not affect the informations which are getting transmitted to the fiber optic cable. System is very prone to noise corruption at this point. However, the development of receivers which incorporate and amplifiers are finding great success in reducing the scale of this noise problem. Transmission characteristics, let us look at. The monomode step index fiber have very simple transmission characteristics because the core has a very small diameter and the light can only travel in a straight line down it. These types of fiber can be sustain only one mode of propagation and requires coherent laser source. Okay, that is a problem because light will be transmitted in a straight line. On the other hand, multimode step index fibers have quite complicated transmission characteristics because of the relatively larger diameter of the core. Many modes can be propagated in the multimode fibers because of the larger core diameter. It is also much easier to launch optical power into the fiber and also the connect the fibers together. Okay, two fibers can be easily connected by together. Moreover, ordinary LED source can be used to launch light. That is most important. I do not need laser. Whilst the transmitter is designed to maximize the amount of light which enters the cable in a direction parallel to its length, some light will inevitably enter multimode cables at the other angles, which is quite obvious, and it is going through total internal reflections and coming to the end, one end. Light which enters a multimode cable at any angle other than the normal to the end face will be refracted in the core, right. It will then travel in a straight line until it meets the boundary between the core and cladding materials. At this boundary, some of the light will be reflected back into the core and some will be refracted into the cladding, right. Now, multimode graded index fibers is also there, where we talked about the step index fiber, both in the case of your monomode and multimode fiber. Basically, this is only graded index. There is a jump of the index, refractive index of the abrupt change of the refractive index of the material of the core or the fiber and also the cladding. Whereas, in the case of graded index fiber, what you will find that the core itself is made of a material where it is changing slowly, okay, slowly, so that the light can go in a curved path itself there, right. So, multimode graded index fibers have a core with non-uniform diffractive index. These fibers are characterized by the curved ray paths, which offer some advantages, but are more expensive than the step index type. So, you will find that next in the lesson 29 we will cover this in more details because what is the passive principle, what is the incident light, all those things, and then we will go to some fiber optic based sensors. With this we come to the end of the lesson 28 of industrial instrumentation.